Every single year, over 80 million vehicles reach the end of their useful lives worldwide, creating a mountain of scrap metal that would stretch from New York to Los Angeles if stacked in a single line. Yet here's what's absolutely incredible. Automobiles are among the most recycled products on Earth, with over 95% of every car getting transformed into new materials that will live again in future vehicles, buildings, and consumer products. A single car contains enough steel to build 15 refrigerators, enough aluminum to manufacture 63 beverage cans, and enough copper to wire an entire house. So how do millions of end-of-life vehicles get completely dismantled and transformed back into the raw materials that will become tomorrow's cars? Today, we're breaking down the extraordinary process inside one of the world's most advanced automotive recycling facilities, where over 2,000 old cars get completely processed every single day, recovering valuable metals while safely handling hazardous materials that could contaminate the environment if not properly managed. Make sure to subscribe as we explore the fascinating technology behind transforming automotive graveyards into treasure troves of recyclable materials. The journey begins at collection points scattered across entire regions, where end-of-life vehicles arrive through multiple channels, including insurance write-offs, fleet replacements, and voluntary owner surrenders. These aren't random junkyards. They're sophisticated operations that must handle vehicles containing fluids, batteries, and components that require careful removal before recycling can begin. Initial vehicle assessment determines the processing pathway for each incoming car based on age, condition, accident damage, and potential for parts recovery. Advanced vehicle identification systems scan VIN numbers while digital photography documents vehicle condition, creating detailed records that enable optimal material recovery while ensuring proper handling of potentially hazardous components. Fluid drainage represents the first critical step because modern vehicles contain over 15 different types of fluids, including engine oil, transmission fluid, brake fluid, coolant, and refrigerants that must be completely removed before dismantling operations begin. Specialized drainage equipment can process multiple vehicles simultaneously while capturing and separating different fluid types for appropriate recycling or disposal. Engine oil recovery systems collect and filter used motor oil that can be reprocessed into new lubricants through advanced refining operations. High-capacity oil drainage systems can extract over 6 quarts of oil from each vehicle while removing contaminants that would interfere with oil recycling processes. The recovered oil often maintains quality levels that enable direct reuse after filtration. Coolant recovery involves capturing antifreeze solutions that contain valuable ethylene glycol, along with additives that provide corrosion protection and temperature stability. Advanced coolant recycling systems can separate coolant from water while removing contamination, creating recycled coolant that meets original equipment specifications for reuse in other vehicles. Battery removal requires careful handling because automotive batteries contain lead and sulfuric acid that present both environmental and safety hazards if not properly managed. Specialized battery handling equipment safely removes batteries while preventing acid spills or lead contamination that could affect worker safety or environmental compliance. Tire removal and processing separates rubber components that can be recycled into new products, including playground surfaces, road construction materials, and industrial rubber goods. Tire recycling systems use mechanical processing to separate steel belts from rubber while creating different size fractions suitable for various end-use applications. Catalytic converter recovery represents one of the most valuable aspects of automotive recycling because these emission control devices contain platinum group metals worth more per ounce than gold. Specialized removal equipment carefully extracts catalytic converters while maintaining the integrity of precious metal-bearing substrates that require separate processing for metal recovery. Interior component removal involves systematic dismantling of seats, carpeting, plastic panels, and electronic components that can be recycled through specialized processing streams. Advanced dismantling techniques preserve material integrity while enabling efficient separation of different polymer types that require different recycling approaches. Airbag system deactivation and removal requires specialized safety procedures because unexploded airbags present serious safety hazards during vehicle processing. Trained technicians use proper tools and techniques to safely remove airbag systems while preventing accidental deployment that could cause serious injuries or equipment damage. Glass removal separates windshields and window glass for recycling into new glass products or alternative applications, including construction materials and industrial abrasives. Automotive glass recycling faces challenges from laminated safety glass that contains plastic interlayers, requiring specialized processing to achieve clean glass separation. Electronic component harvesting recovers valuable materials from automotive computers, sensors, wiring harnesses, and entertainment systems that contain precious metals and rare earth elements. Advanced electronics recycling requires careful component identification and removal to preserve materials that can be processed through specialized electronic waste recycling operations. Refrigerant recovery from automotive air conditioning systems requires certified technicians using specialized equipment that can capture and contain refrigerants that would otherwise contribute to ozone depletion or global warming if released to the atmosphere. Proper refrigerant handling follows strict environmental regulations while recovering materials that can be purified and reused. The systematically stripped vehicle now consists primarily of the metal body structure that contains the bulk of recyclable steel along with aluminum components, copper wiring, and other metals that represent the primary value in automotive recycling operations. This prepared hulk moves toward the mechanical processing systems that will reduce it to manageable pieces suitable for metal recovery operations. The mechanical processing begins with massive automotive shredders that represent some of the most powerful industrial machines on Earth, capable of reducing entire car bodies weighing over 3,000 pounds into fist-sized fragments in less than 60 seconds. These industrial giants use rotating hammers weighing over 500 pounds each, spinning at speeds exceeding 500 revolutions per minute to create the devastating force needed to demolish steel structures designed to protect occupants in high-speed crashes. The shredding process creates an incredible spectacle as car bodies disappear into clouds of flying metal fragments, while the thunderous noise of breaking steel echoes throughout the facility. Advanced sound dampening systems and safety barriers protect workers from the extreme forces, while dust collection systems capture airborne particles that would otherwise create serious health and environmental hazards. Primary shredding reduces vehicles to pieces smaller than 8 inches in any dimension, creating a mixed stream of steel, aluminum, copper, plastic, rubber, and glass fragments that must be separated through sophisticated processing systems. The shredded material, called automotive shredder residue, flows onto massive conveyor systems that begin the complex separation processes needed to recover individual materials. Magnetic separation represents the first major sorting step, using powerful electromagnets that can lift over 50 tons of ferrous metal while allowing non-magnetic materials to pass through unaffected. These magnetic separators operate continuously above fast-moving conveyor belts, extracting steel fragments that represent roughly 75% of the total shredded material by weight. The recovered steel fragments undergo additional processing to remove any remaining non-metallic attachments, while achieving size consistency required for steel mill feedstock. Secondary magnetic cleaning systems remove any ferrous contamination from the non-magnetic material stream, while ensuring maximum steel recovery that optimizes the economic value of each processed vehicle. Eddy current separation systems recover aluminum and other non-ferrous metals using rapidly changing magnetic fields that induce electrical currents in conductive materials, causing them to literally jump away from the material stream. These systems can separate aluminum fragments as small as coins, while achieving recovery rates exceeding 95% for aluminum components. The eddy current process creates fascinating physics demonstrations as aluminum pieces perform acrobatic leaps through the air before landing in collection bins separate from other materials. Advanced eddy current separators can distinguish between different aluminum alloys while simultaneously recovering copper, brass, and other valuable non-ferrous metals that require separate processing streams. Density separation systems use controlled airflow and water-based processes to separate materials by weight and specific gravity. Heavy materials like remaining metal fragments sink in water baths, while lighter materials, including plastics and rubber, float to the surface for separate collection and processing. These systems achieve separation efficiency levels exceeding 98% while handling thousands of tons of mixed materials daily. Advanced optical sorting technology identifies different plastic types using near-infrared spectroscopy that can distinguish between dozens of different polymer formulations in milliseconds. High-speed cameras and computer analysis systems identify plastic fragments moving at over 20 feet per second, while precision air jets separate different plastic types into individual collection streams. Glass separation systems use a combination of screening, air classification, and optical sorting to recover automotive glass fragments that can be recycled into new glass products or used as aggregate in construction applications. The separation process must handle both tempered safety glass that breaks into small cubes and laminated windshield glass that contains plastic interlayers. Copper recovery operations focus on wire fragments that contain high-value copper, along with aluminum wiring and mixed metal component. Advanced separation systems can recover copper wires from complex material mixtures while removing insulation and other contamination that would reduce the value of recovered copper. Quality control throughout the separation process involves continuous monitoring and testing that ensures recovered materials meet specifications for downstream processing. Automated sampling systems collect representative material samples, while laboratory analysis verifies metal purity, contamination levels, and physical properties that affect material value and processing requirements. The separated steel fragments undergo final cleaning and preparation for shipment to steel mills, where they become feedstock for new steel production. Steel preparation systems remove any remaining contamination while creating size distributions optimized for specific steelmaking processes. Clean steel fragments typically command premium prices because they reduce energy requirements and improve quality in steel production. Non-ferrous metal processing creates concentrated streams of aluminum, copper, and other valuable metals that command high prices in commodity markets. Advanced processing systems achieve metal purities exceeding 99% while removing contamination that would reduce material value or create processing problems for metal refineries and manufacturers. Plastic recovery systems sort and clean recovered plastic fragments to create feedstock suitable for plastic recycling operations. Different plastic types require separate processing because incompatible plastics cannot be mixed without creating inferior recycled materials. Advanced plastic cleaning removes labels, adhesives, and other contamination, while preparing materials for reprocessing. Waste processing systems handle the remaining automotive shredder residue that cannot be economically recovered through current separation technologies. This residue, representing roughly 20% of the original vehicle weight, undergoes treatment that recovers additional materials while safely disposing of remaining waste through environmentally compliant methods. Energy recovery systems capture and utilize waste heat generated by shredding operations, while advanced dust collection systems recover fine metal particles that would otherwise be lost. These systems improve overall facility efficiency while minimizing environmental impact through comprehensive waste and emission control measures. The processing facility operates sophisticated material tracking systems that monitor recovery rates, contamination levels, and processing efficiency across all separation systems. Real-time data analysis enables continuous optimization of processing parameters while ensuring maximum material recovery and economic value from each processed vehicle. The final processing stages transform recovered materials into market-ready commodities that meet the exact specifications required by steel mills, aluminum foundries, and other manufacturers who will use these recycled materials to create new products. Quality assurance programs ensure that recovered steel achieves purity levels exceeding 98% while maintaining size distributions and chemical compositions that optimize performance in steelmaking operations. Steel preparation systems create different grades of recycled steel tailored for specific end uses, including construction materials, new automotive components, and appliance manufacturing. Advanced sorting systems can distinguish between different steel alloys while removing any remaining contamination that could affect steel quality or processing efficiency in downstream operations. Baling operations compress loose steel fragments into dense bundles weighing up to 2 tons each, creating shipping forms that optimize transportation efficiency while enabling efficient handling at steel mills. High-pressure baling equipment applies forces exceeding 1,000 tons to create compact bundles that maintain structural integrity during shipping and storage operations. Aluminum processing creates various product grades ranging from mixed aluminum suitable for general foundry use to separated alloy streams that command premium prices for specific manufacturing applications. Advanced alloy identification systems can distinguish between different aluminum formulations, including engine blocks, body panels, and wheels that require separate processing for optimal value recovery. Copper recovery operations produce high-purity copper, suitable for direct reuse in electrical applications, or further refining into new wire and cable products. The recovered copper often achieves purities exceeding 99.5%, while advanced processing removes insulation materials and other contamination that would reduce material value in commodity markets. Environmental impact assessment reveals that automotive recycling prevents the mining of over 40 million tons of raw materials annually, while reducing energy consumption by up to 75% compared to primary metal. Production. Each recycled car saves enough energy to power an average home for over 6 months while preventing massive quantities of mining waste that would otherwise contaminate natural environments. Hazardous waste management systems safely process the toxic materials removed from vehicles, including lead batteries, mercury switches, and refrigerants that could cause serious environmental damage if not properly handled. Specialized treatment processes neutralize or safely contain these materials while recovering valuable components that can be reused in appropriate applications. Carbon footprint analysis demonstrates that automotive recycling provides net environmental benefits through avoided emissions from primary metal production while supporting circular economy principles that minimize waste generation. Life cycle assessments show that recycled automotive steel prevents over 3 times more carbon emissions than the recycling process creates. Economic impact extends far beyond individual recycling facilities, as the automotive recycling industry supports hundreds of thousands of jobs while providing affordable raw materials that reduce manufacturing costs for new vehicles and other products. The industry processes materials worth over $20 billion annually while supporting entire supply chains that include collection, transportation, and downstream manufacturing. Innovation continues, advancing automotive recycling technology through improved separation systems that can recover additional materials while increasing processing efficiency and environmental performance. Advanced artificial intelligence systems optimize separation processes in real time, while predictive maintenance programs minimize equipment downtime and maximize material recovery rates. Research and development efforts focus on handling emerging automotive technologies, including electric vehicle batteries, carbon fiber composites, and advanced electronics that require specialized processing techniques not needed for conventional vehicles. Future recycling systems must adapt to handle hybrid and electric vehicles that contain different materials and hazardous components. Battery recycling operations represent a growing segment of automotive processing as electric vehicles become more common. Specialized battery processing systems can safely dismantle lithium-ion batteries while recovering valuable metals including lithium, cobalt, and nickel that are essential for new battery production while preventing fire hazards and toxic chemical releases. Quality certification programs ensure that recycled materials meet industry standards for purity, composition, and performance characteristics, while providing documentation that enables manufacturers to confidently use recycled materials in new products. Third-party testing and certification create market confidence while supporting regulatory compliance for manufacturers using recycled content. Market distribution systems coordinate sales of recovered materials to global commodity markets while optimizing pricing and transportation logistics that maximize value recovery from each processed vehicle. Advanced market analysis systems track commodity prices while timing material sales to achieve optimal revenue from fluctuating metal markets. Supply chain integration connects automotive recycling operations with manufacturers who use recycled materials as feedstock for new products. Long-term supply agreements provide market stability while ensuring consistent material quality that meets manufacturing specifications for automotive, construction, and consumer product applications. Consumer awareness programs educate vehicle owners about proper end-of-life vehicle disposal while highlighting the environmental benefits of automotive recycling. Educational initiatives promote understanding of recycling processes while encouraging responsible vehicle disposal that maximizes material recovery while preventing environmental contamination. Regulatory compliance ensures that automotive recycling operations meet all environmental, safety, and transportation requirements while maintaining proper documentation for hazardous material handling and disposal. Advanced compliance management systems track regulatory changes while ensuring continuous compliance with evolving environmental and safety standards. This remarkable recycling facility processes over 700,000 vehicles annually, recovering enough steel to build over 100,000 new cars while preventing millions of tons of materials from entering landfills. The operation demonstrates how advanced technology and environmental responsibility can create profitable businesses that benefit both the economy and planetary health. Global expansion of automotive recycling technology helps address growing vehicle waste streams in developing countries while providing economic opportunities in regions where vehicle ownership is rapidly increasing. Technology transfer programs share processing knowledge, while equipment manufacturers develop systems suitable for different scales and market conditions. Future developments in automotive design increasingly consider end-of-life recycling requirements, with manufacturers designing vehicles for easier disassembly and material recovery. This design for recycling approach promises to dramatically increase recycling efficiency while reducing the environmental impact of automotive production and consumption throughout entire vehicle life cycles. And there you have it. The absolutely incredible process of transforming millions of end-of-life vehicles into valuable raw materials that become the foundation for new cars, buildings, and countless other products. The precision, environmental benefits, and economic impact of automotive recycling showcases how advanced industrial processes can turn waste into valuable resources while protecting our planet for future generations. What other recycling technologies would you like us to explore? Drop a comment below and let us know what you think. And don't forget to like, share, and subscribe to keep exploring more fascinating industrial journeys with us.